All right, number 30. So for number 30, what I think I'll do first is, since the ratio test doesn't look here like it's going to work, I'm going to try just the alternating series test first. And I'll go with the second thing first. And remember, I'm focusing my attention on the b sub n only, which is this piece. So the limit as n goes to infinity of 1 over n times natural log of n, that obviously goes to 0. And then the first condition, I have to show it's decreasing eventually. I think I might do that with a derivative. What do I want to do? Let me try it with the inequality. Let me just try 1 over n plus 1, or sorry, 1 over n times natural log n. Is that greater than 1 over n plus 1 times natural log of n plus 1? That's going to be true. Let's see. We have n plus 1, natural log of n plus 1, greater than n times natural log n. Well, this is definitely bigger than this, and natural log of n plus 1 is definitely bigger than natural log of n, and we know that because the natural log function is increasing like this. So if I pick any n, it doesn't matter where it is, the next point, n plus 1, that I pick must be above it. So this left side is definitely bigger than the right side. I think that's good enough to show that it's bigger. So we'll leave it at that. This is convergent then by the alternating series test. The question is whether or not it's conditionally convergent. So let's take the absolute value of this. The absolute value is just this. And I need to show whether or not that is convergent or divergent. So for this one, I would use probably what you want to do. We could do an integral test. We might be able to do a comparison test. Let's try a comparison. Let's compare that to harmonic and hope for the best here. I'm going to compare it to this. This is a divergent, and I'm going to use the limit comparison. Try to avoid using integral test. Integral test I could use because take natural log of n, derivative, that's 1 over n, so I could do an integral on that. But I'll try the limit comparison. Limit n goes to infinity of that piece, 1 over n, natural log n, over this piece, 1 over n. And then this is going to be, that's not going to work. Limit n goes to infinity of 1 over natural log n. So that flips and cancels the n's. That goes to 0. That's not a positive constant. This needs to be a positive number for this to work. So I got unlucky there. How about a comparison test with a direct comparison? So using this divergent one, try and show that a sub n is bigger than or equal to b sub n. So try and show that 1 over n times natural log n is bigger than or equal to 1 over n. And that's not going to work either. So can't use that. So I think the integral test is the only thing I can do. So I have f of x is 1 over x natural log x. Okay, first of all, f is continuous, except at 0 and at 1, but I'm starting at 2, right? So if I plug in 0, it's undefined. If I plug in 1, natural log of 1 is 0. So that's why it's important I start at 2. So it is continuous on from 2 on. It is positive. That's true because this is a positive number. Natural log of anything bigger than 2, or 2 or bigger, is definitely positive. And then now I need to show it's decreasing. Continuous, decreasing. So let me show that f is decreasing. And we already showed that the sequence was decreasing earlier. So this is going to decrease too. So that's decreasing. So now I'm going to set up an integral. So integrate from 2 to infinity 1 over x natural log x dx. I'm going to let u be natural log x. du is 1 over x dx. And this integral then can be rewritten as integral 1 over u du. And then that's just natural log u. And so I'm going to go ahead and say that this is equal to natural log of u, but u was natural log of x, evaluated 2 to infinity. And when I plug infinity in, take a limit or whatever, this becomes infinite, natural log of infinity, infinity. This thing diverges. So since the integral diverges, the series diverges. So here's what we have. The alternating series converged by the alternating series test. But the absolute value of the series, right, the absolute value here, that diverged by the integral test. So this is a conditionally convergent series. Okay, 31. Where's 31? Sum n equals 1 to infinity. Negative 1 to the n, arctan n. I'm going to do arctan like this. Arctan n over n squared. Ooh. Arctan of n. All right. So, I think I'm going to try and get lucky here. I'm going to try and look at the absolute value of this first. And of course, if this converges, then that one will. The thing is, it alternates, and this stuff, as you plug in different values of n, it spits back angles, and those angles could be negative. So we do have some issues there. Yeah, so, all right. Let me see what I want to do with this. No ratio test. How about a comparison test? Maybe I can compare this to 1 over n squared. So let me try this. I know that this is a p series. P is 2, converges. So what I'll need to show is that the absolute value of this, so I'm not even going to look at that, the absolute value of that, which is really just the absolute value of the top over n squared, I want to show that that's less than or equal to, because this one converged, 1 over n squared. And the n squareds cancel. And I've got just arctangent of n is less than 1. That's not true. So if you go back and you look at, remember the tangent function looked like this. That's tangent x, or tangent x. Arctangent of x looks like this. So if I plug in values here, positive n's, right, then the biggest this is ever going to get to is pi over 2, because that's this one right here. A vertical asymptote here becomes the horizontal asymptote here. So no matter what, the biggest this could ever get is going to be pi over 2. So, and I need it to be less than 1. So I'm just going to make a small change. I'm going to change my comparison series instead of 1 over n squared, I'm just going to do pi over n squared. This is still a p-series. It still converges because the constant doesn't matter. And then that changes this right here to pi. And then when I cancel out, I get that this is always less than pi, which is true because that's always, what, less than pi over 2. So that will work. So I have shown that I have a convergent series over here that I'm comparing the absolute value of this one to. And I've shown that all of these pieces are smaller than all of these pieces. So this one must converge also. So since the absolute value converges, this converges. So this is an absolutely convergent series. That's interesting. 32. Sum n equals 1 to infinity, or is it 0? 1 to infinity. Negative 2 to the n over n to the n. And I'm going to rewrite that, because of that negative 2, rewrite that, sum n equals 1 to infinity of negative 1 to the n times 2 to the n over n to the n. And I'm going to rewrite that as negative 1 to the n times 2 over n to the n. Now you might be wanting to do the ratio test because you've got powers of n, but the root test is even better here. And here's why the root test is good. What I'm going to do is I'm going to take the limit as n goes to infinity of the nth root of the absolute value of this. And when I do the absolute value of this, the negative 1 to the n is not going to matter. So I'll have 2 over n to the n. So when I take the absolute value, this goes away, so I'm not going to write it. 2 over n, the absolute value of that is still going to be just this, because this is positive. But then to the n. And that, the root and this go away, I get limit as n goes to infinity of just 2 to the n, or 2 over n. And that goes to 0, which is less than 1. And according to the root test, if that is less than 1, then this is an absolutely convergent series. So this root test shows that this was absolutely convergent. Nice. That worked out real nice. I think 33 is going to be another root test. Limit n goes to infinity. Oh, what am I doing? Sum n is 1 to infinity of n squared plus 1 over 2n squared plus 1 to the n. So again, the whole thing's raised to the n power. So I'm going to use the root test. Take the limit as n goes to infinity of the nth root of the absolute value of that, but that's just, it's all positive in there, so you don't have to worry about the absolute value. The n and nth root go away, which is just limit n goes to infinity of n squared plus 1 over 2n squared plus 1. And when you do L'Hopital on that, you're going to get 1/2. That's less than 1. This is absolutely convergent. And we're done. 34. Sum n equals 2 to infinity. Negative 2n over n plus 1 to the 5n. Well, I already see something. Look at this. Nth term. What's the limit as n goes to infinity of negative 2n over n plus 1 to the 5n? So look at this right here. This right here is infinity over infinity. If you did L'Hopital in there, this is approaching negative 2, and then to the 5n. And so this is going to get huge. It's actually going to switch back and forth with negative and positive numbers, but this thing does not go to 0. So this whole thing diverges. Now you could do the nth root test on this also, but I think that's good enough from what I've shown. All right, 35. Sum n equals 1 to infinity, 1 plus 1 over n to the n squared. This is interesting. Really interesting. So this is also sum n equals 1 to infinity of 1 plus 1 over n to the n, but then again to the n. That's what this would mean, because n to the n, you multiply, you get n squared. So I'm going to do the root test on this. Limit n goes to infinity of the nth root of the absolute value of this, but it's all positive, so 1 plus 1 over n to the n, but all of that to the n. And then this n and this n, root n, cancel, which leaves you with limit n goes to infinity, 1 plus 1 over n to the n still. You still have that one. And this one goes to 1, right? This is 0 plus 1. This is approaching 1 to the infinity. That's an indeterminate form. And this is where you'd come in, you do y on this side, you do natural log here, and you do all this mess, and what you turn out, you figure out that that y is equal to e. And then that's greater than 1. And therefore, by the root test, this is going to diverge. So go back, I mean, we've done this before, this limit. So that's divergent. Okay, 36. Sum n equals 1 to infinity, 2 to the n squared. Over n factorial. Yikes. Wow, okay. Can't take the derivative, so I can't do nth term test. How about a ratio test? Let me try a ratio test. Limit n goes to infinity, absolute value. Let me plug n plus 1 in there. So 2 to the n plus 1 squared, ooh, that's nasty, over n plus 1 factorial over this, but it flips. So n factorial and then 2 to the n squared. This is n plus 1 times n factorial. And then now we have a little bit of a problem. So let's see if this will resolve or not. We've got limit n goes to infinity. All right, this right here I'm going to expand. So I get 2 to the n squared plus 2n plus 1 over, let's see, what was still down here, n plus 1, times, over here, the only thing I had was 2 to the n squared, 1 up here, like that. Then, I'm going to rewrite this as limit n goes to infinity of, all right, this up here is 2 to the n squared times 2 to the 2n times 2. That's what that is. That's kind of cool. Over, and then down here I had n plus 1, and then I had this 2 to the n squared. And these two cancel, which leaves me with that. And now limit n goes to infinity of 2 times 2 to the 2n over n plus 1. And I get infinity over infinity. I can do L'Hopital now because I don't have a factorial anymore. And so what I get is, let's see, if I take the derivative on top, so limit n goes to infinity. Derivative on top, the 2 stays. Derivative 2 to the 2n is 2 to the 2n times natural log 2. That's part of the derivative of a to something. And then times the derivative of what's up there, which is 2. And then all of that over derivative bottom, which is 1. And then this thing goes to infinity, which goes to infinity, which is greater than 1. And since it's greater than 1, by the ratio test, this diverges. All right. What's my time on this one? 20 minutes. All right. I think I've already gone past what I asked you to do, but I want to make a pretty. I want to look at a couple of these that are really kind of neat. Number 37. So we have 1 minus 1 times 3 over 3 factorial plus 1 times 3 times 5 over 5 factorial plus 1 times 3 times 5 times 7 over 7 factorial plus dot, 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 dot. And they tell you that this is negative 1 to the n plus 1, or minus 1. And then 1 times 2 times 3 all the way out to 2n minus 1 over 2n minus 1 factorial. What the hell is this? So we have not seen this before. All right, we have not seen this at all. But let's just try and get our heads around what's happening. We have an alternating series, positive, negative, positive. Oh, I forgot to put negative here, I believe. Yeah, that's negative, negative. And then that thing over there. Don't worry about that right now. So I'm going to rewrite this up here. This first one is 1 over 1 factorial, because 1 on top, 1 factorial on the bottom is 1. This is 1. So look what's happening on top. The first term is 1 over 1 factorial. The second term isn't 3. It's 1 times 3, which is 3, but over 3 factorial. Maybe let's do it this way. Let's look at the bottoms. 1 factorial, 3 factorial, 5 factorial, 7 factorial. That is just odd numbers starting with 1, but factorial. So that's what the bottoms are, and that's where this is coming from. It's an alternating series which starts with positive. They use n minus 1 instead of n plus 1. And then the top is something we have not seen. This is not 3, 5, 7, 9. These are not factorials because they're missing the 2, right? The 4, the 2, the 4, the 6. So it's almost like a factorial. But it's just the product of the first couple of odd numbers. So it's 1 times 3, and then 1 times 3 times 5, and 1 times 3 times 5 times 7. The next one will be 1 times 3 times 5 times 7 times 9. Next one, 1 times 3 times 5 times 7 times 9 times 11. So what's happening is you're doing 1 times, this was a 3, sorry, 1, 3. That's what they had there, right? Yeah, 1, 3. I wrote that down wrong. 1, 3, 5. So it's 1 times 3 times 5. And when do you stop? You stop when you get out to, let's see. Like here I stopped at 3, right? But 3 was the factorial. Here I stopped at 5, but 5 was the factorial. That number down here is where I'm going to stop. So I put 2n minus 1. And what I want to do here is add these up. N equals 1 to infinity. That's my formula. That's my formula for that series. And what I want to know is if it converges or diverges. So in this problem, they actually gave you a big hint as to what the formula was. But in the next problem, I don't think they do that. They don't give you the formula. We have to come up with it ourselves. So again, going back, taking a look, if n is 1, this is 0, negative 1 to the 0 is 1, so it's positive. If n is 1, 2 times 1 is 2, minus 1 is 1. So what I'm going to do is I'm going to multiply the odds, but I'm going to stop at 1. So that's just 1 on top. And then on the bottom, if I plug in n equals 1, I get 1 on the bottom, 1 factorial. So this was a 1, a 1, and a 1. So that works. If n is 2, 2 minus 1 is 1. Negative 1 to the 1 is negative 1. So here's my negative sign. I'm going to stop. I'm going to do 1 times 3 times 5, but I'm actually going to stop when I get to, let's see, I'm plugging in 2. 2 times 2 is 4, minus 1 is 3. So I'm going to do 1 times 3 times 5. I'm going to stop, though, at 3. So I don't go out to 5. I stop at 3. And then this will become 3 factorial. So that's this one. And when n is 3, this is going to be positive. When n is 3 here, I get 6 minus 1 is 5, so I'm going to stop at 5, and the bottom will be 5 factorial, and so on and so forth. So now we have to figure out if this thing converges or diverges. So I'm going to use a ratio test. All right, this is going to be a very interesting ratio test. So what I think I'll do is I'll write this sum up here so we can have it. There we go. All right, so let's use a ratio test on this. So let's take a limit as n goes to infinity of the absolute value. Let's plug n plus 1 into this first. Now the negative 1 isn't going to matter. Negative 1, when I plug n plus 1 in there, I get n. Now times, let's see, the top of this, 1 times 3 times 5, and I'm going to go out to what? I plug in n plus 1 right there. 2 times n plus 1 minus 1 is 2n plus 2 minus 1 is 2n plus 1. So this is, I'm going to stop at 2n plus 1. Then on the bottom, same thing, plug n plus 1 in there, I get 2n plus 1 factorial. Then this over that, which I'm going to flip over here, so that means the bottom is the negative 1 to the n minus 1 times 1 times 3 times 5 times, and I'm going to stop at 2n minus 1. And then the top is 2n minus 1 factorial. These don't matter. And then we have something interesting. All right, this is cool. Let's see what happens here. Let's do the factorials first, because the factorial we've dealt with in the past. Just peeling off, just keep peeling one off of each of those, and that breaks down to be this, this, and this cancel. Now what we need to figure out is what in the world is going on with this thing, all right? So let me write down where we are right now, so we have it all nice and clean. I'm sitting here right now. I'm at a limit as n goes to infinity, absolute value. On the top, the only thing I have is 1 times 3 times 5 times dot, 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 until I get down to 2n plus 1. I'm leaving a space in there for a reason. You'll see in just a second. On the bottom, what I have is 2n plus 1 and 2n. And then these were gone. I have 1 times 3 times 5. So I've got 1 times 3 times 5 until I get down to 2n minus 1. All right. So what's going on here? What I want you to notice is that this right here is an odd number, right? All of these are odd numbers. What is the number that would be right in front of this that I would multiply it by? So let me make sure it's coming out on camera. Ooh, that's really close. Let me move that up. Okay. So this is an odd number. What is the number right in front of it going to be? So for example, if that first number was 111, it's an odd number. The number in front of it would be 109, right? Or if this was 97, the number in front of that would be 95. It's always 2 less than it, right? So what would happen if I take 2 away from this? What's 2n plus 1 minus 2? It would be 2n minus 1. And then what you can see if you do that is that the 1 and the 1 cancel, the 3 and the 3 cancel, the 5 and the 5 cancel, everything cancels all the way until here. These cancel. And so what you're left with is limit n goes to infinity. On top, everything canceled except 2n plus 1. And on the bottom, you have a 2n plus 1 and then a 2n, and everything else is gone. And just so happens that this cancels also. That may not happen every time. And all you're left with is the limit as n goes to infinity of 1 over 2n. And that goes to 0, which is less than 1, so it converges absolutely. That's a cool problem. That's a cool problem. All right, let's look at another one, the next one. All right, we're going to have to come up with a pattern on this one, 38. So we have 2 over 5 2 over 5 plus 2 times 6 over 5 times 8 plus 2 times 6 times 10 over 5 times 8 times 11 plus 2 times 6 times 10 times 14 over 5 times 8 times 11 times 14 plus dot, 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 dot. Wow, okay, so what's going on up top? I'm taking the number 2, right, over the number 5. On the next one, it's 2 and 5 again, but now I multiply by 6 and 8. So do you agree here that if I add 4 to 2, I get 6? On the next one, if I add 4 to 6, I get 10. If I add 4 to 10, I get 14. So what happens is up top, each time I'm getting 4 more than the previous one. And on the bottom, it's 3 more, right? 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. So there's got to be a way I can come up with a formula for this. I'm doing a sum. N is equal 1 to infinity. And on the top, what I'm doing is I'm doing 2 times 6 times 10, and I'm doing this until I get out to a certain thing. So how about, I know that I go up by 4 each time, so how about 4n? Now, if I try and plug in 1, I need my first number to be 2. So if I plug in 1 here, I'm going to get a 4. So I need to take 2 away from this. Let's see if that works. If I plug 1 in, I get 4n minus 2. So 4 times 1 is 2, minus 2 gives me 2. So I'm going to multiply 2, 6, 10, but I'm going to stop at 2. So it'll just be 2. Then when n is 2, I get what? 8 minus 2, which is 6. So I'm going to go 2 times 6 and stopping at 6. So that'll give me this. And then when n is 3, I'm going to go, what, 12 minus 2 is 10. So I'm going to go 2 times 6 times 10, right, but I'm going to stop at 10. When n is 4, I get 16 minus 2 is 14. So I'm going to go 2 times 6 times 10 times and stop at 14. So that'll be this one. Same exact pattern on the bottom. 5 times 8 times 11, and I want to do that until I get out to what? So we said these were each going up by 3, so I'm going to use 3n, and I need to start at 5. So when I plug in 1 here, I get 3, so how about if I add 2 to that? Check it. Plug in 1, you get 5. Plug in 2, you get 8. Plug in 3, you get 11. So the important thing is that you cannot just use this. This is not it, because when I plug in 1 here, I get 2 over 5. And then you'd say plus, and now you plug in 2, and you would get 6 over 8. But that's not creating this. It's this dot dot thing in front that shows you that there is a pattern of multiplication that must take place every single time you change your end. Really interesting. I hope you think it's interesting. I think it's cool. All right, so let's try the ratio test again. See if you can keep up with this. Limit, n goes to infinity. All right, I need to plug n plus 1 in here and n plus 1 in here. So it's 2 times 6 times 10 times dot, 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 dot. And I'm going to stop out here when I plug n plus 1 in right there. So 4 times n plus 1 minus 2. That's 4n plus 4 minus 2. This is 4n plus 2. 4n plus 2. Now remember that the one right before it will be 4 less than it. So the one right before it is 4n minus 2. Just keep that in mind. Over. Now I need to do the same thing here, but plug in n plus 1. So 5 times 8 times 11 times dot, 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 dot. And now plug n plus 1 into this. 3 times n plus 1 plus 2 is 3n plus 3 plus 2 is 3n plus 5. All right. And then, is that right? Yes. All right. And then the one right before it is 3 less than, right? Because each one of these is 3 less. So this would be 3n, 3 less plus 2. OK, that's what I get when I plug n plus 1 in. Now I divide this by just that, which means I flip it and put it over here. Damn it, I'm going to run out of room. So when I flip it and squeeze it in here, let's see if I can. You know what I'll do for this problem only? I'll just move my camera a little bit. Hopefully it'll stay in focus. All right, so just this thing, but flipped. So I got 5 times 8 times 11 times dot, 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 3n plus 2. And then the other one is 2 times 6 times 10 times dot, 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 4n minus 2. And hopefully you see how important it was for me to pick up these red ones, because this shows me the cancellation. Like 2, 2, 6, 6, 10, 10. And then everything in between all the way to this, gone. And then on this one, 5, 5, 8, 8, 11, 11. And then this and 3n plus 2, 3n plus 2. The only thing left at the end of the day here is this right there. So what I get is that this limit, let me get my camera back to where it needs to be. My limit as n goes to infinity is 4n plus 2 over 3n plus 5. And L'Hopital, once on that, gives you 4/3. It's bigger than 1. That series diverges by the ratio test. Should we try 39? So 39, they give you a formula. That's nice. Sum equals n equals 1 to infinity. And so we've got a pattern on top. The pattern is 2 times 4 times 6 times dot, 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 till I get out to 2n, and then over the bottom, which is just n factorial. Okay. So when n is 1, well, I'll write out what the first few pieces would be. If n was 1, I would do this pattern till I get out to, let's see, n is 1, until I get to 2. So it would just be 2 over 1 factorial. Plus, the next one, I would go n is 2, so 4, I do 2 times 4 until I get to 4, so 2 times 4 over 2 factorial. Plus, the next one would be 2 times 4 times 6 over 3 factorial. And then 2 times 4 times 6 times 8 over 4 factorial, and so on and so forth. So I'm trying to figure out what's going to happen with this. I think a ratio test might be in order here. Ratio. Limit. N goes to infinity. Let's do it. All right, so I'm going to do this, but n plus 1 plugged in. So I'm going to stop at 2. Give myself a little bit of space here. I'm going to stop this at 2n plus 2. So when I plug in n plus 1 right there, distribute the 2, I get this. The one right before it is 2n over the bottom, but with n plus 1 plugged in. So I'll go ahead and peel off the n plus 1 and do that. Then divide this by this, but flip it. So n factorial here. And then I have 2 times 4 times 6 times dot, dot, all the way to 2n. And you can see all this cancels with this. The n factorials cancel. And so what you're left with is the limit as n goes to infinity. The only thing left on top is 2n plus 2. The only thing left on the bottom is n plus 1. L'Hopital on that once, 2 greater than 1, divergent series. These are actually kind of fun. I didn't say that again, did I? All right, 40. I'm going to do 40. This may be my last one. What's my time on my thing? 42 minutes. Okay, I'm doing good. 40. They give you a formula? Yes. Sum n equals 1 to infinity, and then negative 1 to the n, alternating series. The top is 2 to the n, n factorial over, now the bottom is a pattern, 5 times 8 times 11 times dot, 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 until I get out to 3n plus 2. Ratio test. Limit, n goes to infinity. Oh, okay. I'm not going to worry about this because that's in the ratio test, that absolute value is going to kill it. So I'm going to do n plus 1 here and here. So 2n times 2, that's there. The n plus 1 factorial is going to become n plus 1 times n factorial over this thing, pattern, 5 times 8 times 11 times all the way out to, let's see, what do I get when I plug n plus 1 in there? 3 times n plus 1 plus 2, 3n plus 3 plus 2, so 3n plus 5. I gave myself some room to get the one right in front of it because I think that one's probably going to cancel. It's always 3 less, so this is 3n plus 2. And now divide this by this, again, not caring about the negative, and that means flip it. So I'm going to have over here the 5 times 8 times 11 times all the way out to 3n plus 2, and then on the bottom 2 to the n, and then n factorial. Lots of cancellation here. N factorial, 2 to the n, 2 to the n, 5, 5, 8, 8, 11, 11, all the way to 3n plus 2. So what I have left is the limit as n goes to infinity of the only thing left on top, I had a 2 and an n plus 1. On the bottom, everything's gone except 3n plus 5. And if I take that limit and do L'Hopital, I get 2/3, which is less than 1. This converges absolutely by the ratio test. Okay, that's it. Hope you enjoyed.